I'll be presenting my summary on neural discrete representation learning. It's a paper out of DeepMind. And basically, this paper introduces a new class of variational autoencoders called as vector quantized variational autoencoders, or VQ-VAEs. The main difference in these autoencoders compared to the traditional variational autoencoders is that the latent space is discrete rather than continuous, and you're learning as a prior rather than having a static prior. So these are the two contributions. And according to me, the main objective of this paper is to introduce this idea or this paradigm of training the VQ-VAE end to end, and then learning an updated prior on the latent space. So hopefully by the end of this talk, we should get a better idea of what this means. So I think before we get into what a VQ-VAE is, it's helpful to understand what the limitations of VAEs are, what the limitations of autoencoders are. So let's just go through that first. So autoencoders, in an autoencoder, basically you have an image which is fed to an encoder. You generate a latent representation which is fed to a decoder, and then you get the reconstructed input. Now you're calculating the reconstruction loss between the reconstructed input and the original input. So your loss is only the reconstruction loss over here. Now, the reason I want to talk about autoencoders is because of the messy latent space autoencoders have. And this messy latent space does not lead to generation. So if you see, the yellow dots might be points which are similar to each other, but they occupy different positions in the latent space. So this is not good for generation. Ideally, you want your similar points to be close to each other. You want your dissimilar points to be far apart, and you want them to occupy a fairly compact volume in the latent space. Yeah.
I just wanted to ask, why do they take different places in the space and why are they not too close to each other like
Yeah.
equivalent embeddings?
So the reason for this is because autoencoders do not have any prior imposed on them. And VAEs enforce this probabilistic prior, and this leads to a latent space which is more structured.
Okay.
So what variational autoencoders basically do is they enforce this probabilistic prior, and this gives the latent space certain properties. Semantically similar objects are close to each other, dissimilar far apart, and it occupies a fairly compact volume in your latent space. So this is how the latent space of a VAE would look like compared to an autoencoder latent space. And the only difference here is that you're enforcing this probabilistic prior. Now this can facilitate generation, and VAEs are able to generate diverse samples because of this structure in the latent space. So the loss function for a VAE has this additional term called as a regularization term, which is basically calculating the divergence between the posterior, the approximation of the posterior, and the prior. So basically what we're doing here is we're trying to push the latent codes to this prior, which was setting before training. And this prior is generally a standard normal distribution. So we're trying to enforce our latent space to this standard normal distribution.
Can you talk about why do we enforce it to standard normal distribution, and why not any other kind of distribution?
So the reason for a standard normal distribution is because it has all the properties that we want for to facilitate generation. So that's the reason we go for this.
Okay.
So yeah, the reconstruction error pushes the reconstructions close to input.
Properties as in mean of zero and variance of that?
Yeah.
Okay.
And the regularization term ensures a smooth and well-structured latent space. But it's important to ask a couple of questions on VAEs, or it's important to look at the drawbacks of VAEs. So the first drawback is posterior collapse. In very simple terms, posterior collapse is a phenomenon in which the decoder is ignoring the latent codes. So this results in very limited diversity and poor quality in the generated samples. So let's try looking into a bit more detail of what this means. As mentioned before, our loss function contains this regularization term, which is trying to reduce the divergence between the posterior, the approximated posterior, and the prior. So for example, if you see Q of Z of X, it's our posterior, it's our latent code. And what this KL divergence term does is it tries to push it to that P of Z, or the standard normal distribution. But sometimes what might happen during the training process is that the KL term pushes too hard and the posterior collapses into the prior. Hence the term posterior collapse. So the posterior is essentially falling into the prior, and you lose this conditioning on your observations or conditioning on X.
So would that mean that like if posterior collapses into the prior, then posterior also will have the same properties as prior, like it will also
Yeah.
have normal distribution?
Exactly. And in certain situations, that's not ideal because you're losing the conditioning on your observation. So you're only looking at the prior now. So Q of Z of X becomes Q of Z because you're losing the conditioning on the observation, and Q of Z becomes P of Z. So in that situations, you're going to have very limited diversity, and you're not going to generate samples which are true reconstructions of your input. Also, what we've seen in VAE is that we are enforcing the standard normal distribution. This actually has a lack of flexibility because imagine your actual input data is multimodal. By enforcing the static prior, what happens is that you're not able to represent the true diversity in your data distribution. So is a static prior a good thing? May not be in certain situations because you're limiting the flexibility in the generation process.
So when you say it's not good in certain situations, is it good in a certain kind of situations as well?
Yeah, if your input distribution is not very diverse, if you think it can match that standard normal distribution or any other prior you're imposing, it might be a good choice.
Or if the goal is to reconstruct things that was similar to the training data.
Right. So okay, in those situations, it might be a good option. Also, are continuous spaces always better than discrete spaces? If you actually look at some of the real world situations, a lot of real world data favors a discrete representation rather than a continuous representation. For example, images can be represented in terms of vectors. You can have text which can be represented in terms of vectors. And also a number of algorithms are designed to work on discrete data. For example, transformers are designed to work on discrete data. So it can be favorable to have discrete latent spaces compared to continuous latent spaces. So it is an example of how an image can be represented as discrete codes. So that's the motivation behind VQ-VAE. We want discrete latent representations. We want a prior which is learned rather than static. And we want an architecture which does not suffer from the posterior collapse phenomenon. Now let's quickly go through the methodology. So first I'll talk about the model architecture. And I think it'll be helpful to explain the architecture by running through an example. So in this particular example, we're feeding an image to an encoder, and we're generating the output of the encoder Z of E of X. Now this encoder output, each vector in our encoder output is compared to a set of codebook vectors. So basically we're trying to find the codebook vector which has the least distance from the encoding vectors. And that distance is calculated using the Euclidean distance or the L2 loss. So this is basically a similarity measure, and you're trying to find the index of the codebook vector, which has the least distance with the encoder vector. And then you fill it in your Q of Z of X or a posterior. So a posterior here essentially is a matrix of numbers or a matrix of indices. And the index corresponds to the embedding in the codebook, which has the least distance with our encoder output.
So is that done for the each block? Because in this diagram it shows that like for just 1, 3, 2, and 53 we are
Yeah,
matching with it.
you'll have a dense matrix. It's done for each block. I think over here, just for an example, they have it in this format. So this is essentially how it would work. You pick a vector in your encoder. Maybe E3 has the least distance. And then you place the index 3 in that corresponding position in your posterior. After that, you reconstruct or you construct your decoder input using these indices. So using these indices, you construct the codebook vectors you arrange the codebook vectors into a set of matrices which you feed to your decoder. Now, this is the forward pass, but we also have to look at. So we were talking about the forward propagation. Now let's talk a bit about the backward propagation. There's a problem here when it comes to the backward propagation, and that is the argument function. It's going to be non-differentiable. So that means you cannot calculate the gradient for it. So what we do here is that we copy the gradients for the decoder input and paste it onto the gradients for the encoder output. Now we do this through straight through estimation. And the idea is that this can work in practice because the decoder inputs should be close to the encoder output, or the encoder output will be close to the codebook vectors. Now, how do we enforce it? We enforce it using the loss function. So the first term in this loss function is familiar to us. It's the reconstruction loss. The second term is the VQ loss, which pushes the embedding space close to the encoder output. Then we also have a commitment loss, which pushes the encoder output close to the embedding space. So if you can see in this loss, we have something called SG, which means stop gradient, which basically removes that particular component from the computation graph and kind of like freezing that particular layer. So we're only updating the embedding vectors in the case of VQ loss, and we're updating the encoder vectors in the case of commitment loss. So this basically what it does is it's pushing the embedding vectors close to the encoder output and the encoder output close to the embedding vectors. And in this manner, we can paste the gradients for the decoder input onto the encoder output, and it works in practice.
So why is there a need to calculate like both these things separately, and like why are we fixing one of them and then pushing the other towards the fixed one in two terms? Like why can it not be done in a single?
Right. So basically, you want to keep it, you want to hold it in place, and you want to push the encoder close to it, and the decoder, the embeddings, you want to hold it in place, and you want to push the embeddings close to it. So I don't think there's really a theoretical concept behind it. I think empirically it worked. That's why they went ahead with it. Now, if you look at the loss function, the first term in the loss, which is the reconstruction loss, the encoder and decoder are both responsible for it. The second term, which is the VQ loss, that for that loss, the codebook is responsible for that loss. And the last loss, the encoder is responsible for it, which is the commitment loss. So basically, you have three sets of parameters which you're learning: the parameters for the encoder, parameters for the codebook, and parameters for the decoder. So this is the first step in the training process. You're training the vector quantized variation autoencoder end to end. The next step comes in learning the prior. So during the training process, you're actually imposing a uniform prior. What this does is it gives each code a uniform probability of being selected. After the training process is completed, you can remove this constraint and you learn a new prior over this latent code distribution. What this gives us is the ability to generate new data by sampling from this prior. So what you do is you sample from this prior, you feed it to your decoder, and your decoder can generate more diverse samples and more novel data. So this is the second step in the training process. So just to give you an overview of the overall training process.
Could you please explain like how we are fixing the prior for the training phase and how is it being changed after training? I thought like we change it during training and not after.
No, so you maintain that uniform prior during the overall training of the VQ-VAE end to end, and after the training is done.
Put this constraint?
So if you remember, they say that you're maintaining the you can remove the KL divergence term because your posterior is going to be deterministic. It's not stochastic, and in that manner you can enforce the uniform prior.
Right.
So the overview of the training process basically is you train the encoder model end to end. Then you train an autoregressive model on the discrete latent space to generate new and novel data. So in this particular paper, they talk about two autoregressive models. They talk about the first one being pixel CNN, and the second one is WaveNet. Pixel CNN is for images, WaveNet is for audio. And the idea is that this distribution can capture long-term dependencies and structures present in the latent space. So the second step in the training process can be a bit difficult to understand. So I just wanted to break it down a bit. So in the case of images, we get this posterior categorical distribution after we pass an image through the encoder and we compare it with the code books. Then what you do is you flatten out this posterior. So in this case, I've flattened out the posterior. And suppose you have a 32 by 32 posterior, you'll have 32 by 32 numbers flattened out. Then what you can do is you can train an autoregressive model on this sequence. So it's similar to language modeling. What over here, what you're trying to predict is the index at time step t, given all the previous indices that we have seen. So this is how we go about the training of the learning of the new prior. And we can also go about generation by sampling from this prior, constructing this posterior, and then feeding it to the decoder. And the decoder will end up generating more novel samples. So that's an overview of the second step in the training process. So in this paper, they carried out experiments on images, audio, and video. I'll first talk about the audio experiments. Sorry, I'll first talk about how VQ-VAE does reconstructions compared to its other continuous counterparts. So in this experiment, what they do is they basically compare a VQ-VAE with two other generative models, VAEs and WIMCO. They compare it on the CIFAR 10 data set, and they see how good the reconstructions are. And as you can see, VAEs do well. Their compressions is close to VAE. It's not as good. So the lower the bits per dimension, the better the compression is. So VQ-VAEs are comparable to VAEs. So you can say that even though you've created this discrete representation, the reconstructions are close to the continuous representations. That's the main conclusion from this experiment, which can be drawn. The next experiment which they carried out was on audio. So basically what they did here was they took waveforms, they fed it to the encoder, they got their discrete representations, they did their vector quantizing, and they created discrete latents, which they used to condition a wavenet decoder. Now using this wavenet decoder, they were able to generate samples. Now the samples which were generated, they didn't have the same waveform as the original sample. And they didn't even have the same prosody, which basically means the pitch or the places in the sentence where you're putting more emphasis or stress. But what they noticed was that the samples had the same content. So I'll just play a couple of samples for you. This is the first one would be the original sample, and the second would be the reconstructed sample.
Okay, October 16th. Do you want to save this?
Now the reconstructed sample.
Okay, October 16th. Do you want to save this?
And I'll play one more example for you.
Every day at 6:35. Every day at 6:35.
So you can see that the content is the same, but the way the message is being outputted is different.
Okay, October 16th. Do you want to say? Okay, October 16th. Every day at 6:35. Every day at 6:35.
Sorry about that. Yeah. So the conclusions drawn were that the reconstruction of speech using VKE show that different waveforms, that the outputs had different waveforms and different prosody, but the content remained the same. And this gives us the idea that the VQ-VAE is focusing on semantic content rather than the shape of the waveform. So that's the audio experiment. They also do a couple of image reconstructions and generations. They do 3 sets of experiments here. I'll just quickly go through them. The first one is reconstruction. They use VQ-VAEs to reconstruct images. And this is how the reconstructions look. The reconstructions are not great. They have some sort of loss in it. But in the paper, they talk about using perceptual loss to improve the reconstructions.
So are these reconstructions during training?
No, after training, they sample some images and they feed it, and that's the output. They use it, the ImageNet data set for this.
Okay, so I actually have a doubt.
Yeah.
So at inference time,
yeah,
do we provide some input to the encoder and then generate something, or do we simply sample from the representation that we have and then feed it to the decoder?
So when you're doing reconstruction, you would just feed it to the end-to-end VQ-VAE model. So you feed the image and you get the reconstruction from the decoder. But if you want to do generation, you've got your new categorical distribution. You sample from that categorical distribution, you generate your posterior, and then you feed it to your decoder.
Okay, so here our objective was to show
Reconstruction. Yeah. And in this experiments, they have two objectives: to show the reconstruction and the generation process. So this is the generation process. So as I mentioned, they're sampling from this from this prior, and they're creating this new discrete latents, which they're feeding to the decoder. And the decoder is generating the output. And if you see the generations, it has some sort of psychedelic effect in it because you're moving across the latent space. And yeah, these are just a couple of examples of the generations from the ImageNet dataset. What they also did was they used VQ-VAEs hierarchically. So basically, they have an image which is fed to an encoder, which is again fed to an encoder. You're pushing it down to through three global latents, and then you feed it to the pixel CNN decoder. You generate your discrete latents, and then you feed it to a decoder and you generate your image.
I have another doubt.
Yeah.
So you showed in the example of audio that the words that were generated were not different, just the tonality was different.
Yeah.
Similarly, in case of images, the objects essentially were the same. In the
high level structure is maintained.
Yeah.
Yeah.
So is there a way that is there a way of controlling that, wherein you control whether these high level structures are to be preserved or not? For example, in can I use VQ-VAE to change words but to keep my tonality the same, or any such scenario?
I'm not exactly sure about that, but I think overall the conclusion was that you are only able to maintain the high level semantics. So I'm not sure if you can exactly preserve those, the things which you're talking about. They also carried out experiments on videos, and this is basically a sequence generation. They fed the model a couple of frames, and this is the sequence which got generated. So the main conclusion which can be drawn is that VAEs are able to achieve likelihoods that are almost as good as their continuous counterparts, which can be seen through the experiment on the CIFAR10 dataset. VQ-VAEs are also capable of learning meaningful and semantically rich representations, which capture the high-level features while being invariant to low-level variations. This paradigm of training of a VQ-VAE and then learning an update with it prior has been pretty popular. And if you see a lot of the popular generative models right now, they use this paradigm of training. So for example, OpenAI's Jukebox or OpenAI's DALI, they use this form of training. So VQ-VAE is the building block for a lot of popular generative models that we see today.
So all those papers have used discrete representations instead of...
Yeah, discrete representations. And they use transformers rather than, I think we talked about pixel CNN and WaveNet decoder. They use transformers.
For encoding and decoding.
No, they use transformers. So once you've got the category, once you've got the prior, which is learned, the new learned prior, you use an autoregressive model on it. So they're using transformer as the autoregressive model instead of pixel CNN. So yeah, I guess that's about it. Do you have any other questions?
No, that's all I have. Thank you for the presentation.
Yeah, thank you.